Think about AI that doesn't just sit on a server somewhere, but actually, lives in our world. We're seeing things like smart glasses giving you cooking tips in real time, or maybe a virtual companion on your phone that's actually pretty good at offering emotional support. AI is becoming more than just, a voice assistant or text on a screen. It's getting physical, interacting with us and our surroundings in a real way. So today, we're doing a deep dive into something called embodied AI agents. And these aren't your standard AI programs stuck in the cloud. No, these are AI systems that actually have a visual, virtual, or even physical form. This lets them learn and genuinely interact with us and the world around them. It feels like a pretty big shift, doesn't it?
It really is a fundamental shift, and our exploration today, it's based on a really fascinating cutting-edge research paper. It lays out where we are now with these agents and where they might be heading. It's quite a look into the tech and the big questions involved.
Okay, so our mission for this deep dive is to really unpack what these embodied AI agents are. We want to explore what they're doing now, what they might do in the future, look at the incredible tech making it happen, and importantly, get into the ethical side of things, because we definitely need to think about that.
Absolutely. It's a lot to cover, but yeah, it's a fascinating journey.
So let's start with the basics. What is an embodied AI agent at its core?
Okay, so an embodied AI agent is essentially an AI system that is instantiated, meaning it exists in some kind of visual, virtual, or physical form. And this form allows it to learn and interact, not just with the user, with you, but also with its surroundings, whether that's physical or digital.
Right, instantiated. So how different is that, really? I mean, for an AI to truly understand its environment versus just, say, following code, especially in the real world. It's not just a chatbot, like you said, or a drone someone's flying remotely.
Oh, it's worlds apart. Think about trying to cross a busy street. A simple instruction might be, go straight. But an autonomous agent, one that understands the environment, it sees cars, pedestrians, reads traffic lights, maybe even tries to guess what people will do next.
Yeah.
And it adapts its path constantly. That adaptability, that's the core difference.
Okay, that makes sense.
And this embodiment, it serves a few key purposes. Obviously, physical interaction is one, but it also seems to enhance the human-machine connection. It builds more trust, makes interaction more engaging, maybe more empathetic, and perhaps most interestingly, it opens the door for these agents to learn almost like humans do, through rich sensory experience.
It feels like we've jumped from just reactive chatbots, the early Cirrus and Alexis, to something much more proactive. Agents that collaborate. Is it just about bigger models like LLMs and VLMs, or is there something more fundamental, maybe counterintuitive, that enabled this leap?
That's a really good question. It's not just about scale, though that helps. I think the really surprising thing, the insight, is how these models started building their own internal representations, these world models we'll talk about. They learn statistical patterns that somehow reflect how the world works, even though we didn't explicitly program that physics engine in.
Oh, okay.
It's this kind of emergent understanding, not just being good at a specific task. That's the big leap. So now these agents can tackle complex, multi-step jobs. They figure out the steps, anticipate needs, even work with other systems. And crucially, this requires planning and acting, which hinges on this idea of world modeling.
World modeling. Okay, yeah, that sounds pretty futuristic. Let's get into the three main types of these agents the paper discusses. Maybe start with virtual embodied agents, VEAs.
Sure. VEAs, virtual embodied agents, they can show up in lots of forms. Maybe a 2D avatar on your screen, a 3D one in VR, or even quite advanced robotic androids, with actual motors for facial expressions, lip movements, trying to convey emotion.
Wow. Yeah, they've come a long way. The paper mentions some really interesting uses, like AI therapy, agents like Wobot or WISA doing cognitive behavioral therapy. That seems significant.
It's definitely significant in a sensitive area, for sure. Beyond therapy, VEAs are becoming big in the metaverse and mixed reality spaces. They can be your guide, a mentor, even just a virtual friend in places like Second Life or Horizon Worlds. They make those worlds feel more immersive, more alive. You even see non-player characters, NPCs, starting to interact realistically with each other.
That adds a whole new dimension. And then there's AI studio avatars for movies, games, creating characters that seem emotionally real, plus potential in education, customer service, healthcare, lots of areas.
Exactly. Personalized learning, more empathetic customer support, patient assistance.
Yeah.
The applications are broad.
So how do they pull off the emotion part? Is it just like coded smiles and frowns?
It's getting much deeper than that. It involves fields like affective computing, which is about canalizing human emotions in social robotics. Take Fair's Seamless project. They're aiming for avatars that are genuinely emotionally accurate. Facial expressions, gestures, body language, the whole package.
Ah,
Well, they use something called dyadic foundational models. Think of models trained specifically on interaction data, like the seamless interaction dataset that's over 4,000 hours of real human conversations. By analyzing all that, the models learn the really subtle stuff. Active listening cues, how people synchronize visually, the rhythm of turn-taking in a chat. It's learning the dance, basically.
learning the dance from data. Okay. That leads nicely into the next type, which feels even more integrated into our lives. Wearable agents. These seem to really blur the lines.
They absolutely do. Wearable agents are unique because, well, you wear them. Smart glasses, maybe other sensors. They've got cameras, mics, sensors capturing the world from your perspective. Egocentric perception.
Egocentric perception. So they see what I see, hear what I hear.
Exactly. And that's a huge deal. The AI learns from your specific viewpoint, enabling super personalized help.
Mm.
But yeah, it also means dealing with this constant stream of subjective, messy, real-world data. That's a massive AI challenge in itself.
Right, like the Meta AI glasses, they let you ask Meta AI about what you're seeing or control apps.
Precisely. And their main roles tend to be coaching and tutoring. Coaching is more about physical tasks, walking you through a recipe while in your kitchen, helping assemble furniture. Tutoring is more cognitive, helping with a math problem, guiding you through software.
So my glasses could literally coach me through fixing the sink step by step. But does that actually work well? Planning complex real-world actions over time, LLMs sometimes hallucinate.
Yes, that's a major hurdle, yes.
Yeah.
Standard LLMs and VLMs aren't always reliable for long-term action planning in the physical world. They can get details wrong or make things up. They're mostly being to predict the next word or pixel, not necessarily a whole sequence of physical steps.
So what's the solution?
Researchers, like those at Meta, are looking at different approaches to world modeling, things like JPEG joint embedding predictive architectures. The idea there is, instead of just predicting the next thing, the model learns by predicting missing parts of the input from other parts. It helps build a more robust internal understanding of how things relate. This seems to make planning more efficient and reliable. They're also training models to figure out your goal directly from what you're seeing and doing for proactive help.
The potential sounds huge. Personalized learning, real-time help in healthcare, science. All right there, visually overlaid on your world.
Yeah, it's about augmenting human ability.
Yeah.
Making knowledge and assistance immediate and context-aware wherever you are.
Okay, and the third pillar, robotic agents. This is probably the classic sci-fi image, right? Robots walking around?
It often is, yeah. Robotic agents are AIs operating robots in the physical world. Could be autonomously, could be collaborating with people. And we're focusing here on general-purpose robots, not just factory arms doing one repetitive task.
General purpose. So they could do lots of different things.
That's the goal. Their form varies humanoids, with arms and legs, or maybe just arms on wheels or other specialized forms.
And the potential impact beyond, like, robot vacuums. What could they really change?
Oh, potentially a lot. Addressing labor shortages in tough jobs, physical or mental, deploying into disaster zones for rescues where it's too risky for humans, supporting elderly care, helping out in busy hospitals, freeing people from household chores.
Okay, freeing me from chores sounds good. But if they're doing mentally demanding jobs too, that raises big questions about human work.
It certainly does.
And why does the robot need a body to learn effectively? Can a powerful AI just learn everything from data on a server?
That brings us right to the embodiment hypothesis.
Yeah.
The core idea is that actually interacting with the real world through a body is maybe essential for an AI to develop truly general intelligence, to really reason about the physical world. It's the idea that learning through sensing and acting, like humans and animals do, might be the key to something like AGI, artificial general intelligence. Learning by doing.
Learning by doing, not just observing. Okay, so what specific abilities does a robot need? What's the physical side versus the brain side?
Right. Physically, they need locomotion, moving around effectively, dealing with different terrain, stairs, obstacles, especially for legged robots. Then navigation planning, how to get from A to B efficiently and safely. And dexterous manipulation. That's interacting purposefully with objects, grasping, moving things, fine motor skills like using a key or plugging something in. That's really hard.
Okay, those are the physical challenges. What about the brain part, the intelligence needed?
For the brain, a big one is generalization. Being able to do a task in a new place, with new objects, adapting like we do. Also, efficient and lifelong adaptation, learning new things quickly from little data without forgetting old skills. Personalization comes in here too. They need good spatial and temporal memory, remembering layouts, where things are, what step they're on, past interactions. Understanding language instructions and planning is key. Breaking down clean the kitchen into actual steps. And finally, interaction with humans and other agents. Taking instructions, asking clarifying questions, helping physically, working together, maybe even inferring intent.
Wow, okay. That's a lot required for both body and brain. So we've mentioned world modeling a few times now. This seems like the core intelligence. Can we unpack that a bit more? How do they understand the world?
Yes, world modeling is absolutely central. It's the agent building an internal predictive model of its environment. This internal model is what allows it to reason, decide, adapt, act effectively. It leads to better performance, better safety. Without a good world model, the agent is just reacting blindly to immediate sensations. It can't really plan or anticipate.
Okay, so what kinds of world models are there? Is it just one big model?
Primarily, the paper discusses two main types. First, there's the physical world model. This is the agent's internal representation of the external physical world. Objects, their properties, shape, size, color, how they relate in space, how things move, change over time, and critically, cause and effect grounded in physics. If I push this, it will likely fall. That kind of understanding.
Right, understanding physics makes sense for interacting with the physical world. But then you mentioned a mental world model. That sounds different. Like understanding minds. How does an AI even start to model minds?
Yeah, it's a huge leap, conceptually. This gets into AI trying to develop a theory of mind. Now, it's not about consciousness or feelings in the human sense. It's about building models that let the AI infer and predict the mental states of humans or even other AIs.
Simulating what we might be thinking or feeling.
Exactly, simulating it to interact more effectively. This mental model would include things like beliefs, what someone knows or thinks they know, goals, what they want, intentions, their plans, emotions, their likely affective states, social dynamics, understanding communication, both verbal and nonverbal.
So if an agent has this mental world model, it
Yeah.
could anticipate what I need before I ask.
Precisely. It could anticipate user goals, offer help proactively. It could understand if there's a misunderstanding, like you think your keys are on the table, but the agent knows they fell behind the couch.
Ah,
It
okay.
could predict emotional responses, maybe adjust its tone or approach to be more empathetic. Ultimately, it makes human-AI collaboration much smoother, interaction more effective, and allows for more strategic conversation.
Understanding physics and minds. That's quite the challenge. So how are these world models actually built? What are the key components inside the AI?
Well, these models essentially integrate several key functions: multimodal perception, planning for physical and cognitive tasks, memory, and action control. Let's start with perception. Agents have to perceive the world to act. For vision images and video, they rely on sophisticated general-purpose vision language models. There's usually a component, often called a perception encoder or PE, that acts like the AI's visual cortex, turning raw pixels into a rich, abstract understanding.
Okay, vision. What about sound? Especially for wearables.
Audio and speech are vital, yeah.
Yeah.
Detecting ambient sounds, tracking conversations, knowing when someone's talking to the agent, and generating speech back. The challenges are huge.
Yeah.
Background noise, different accents, dialects, limited processing power on tiny devices. Future work is looking at edge AI, processing locally for privacy, plus better personalization and handling more languages.
Makes sense. And touch. For robots interacting physically.
Touch is critical. It complements vision, especially when vision is blocked, maybe reaching into a bag. It gives feedback on contact, force, texture, lets the robot estimate force, detect if something's slipping, recognize materials. It's essential for delicate manipulation.
So they perceive through multiple senses, build these world models. Then how do they actually act? How does a virtual agent gesture or a robot move?
The action control part differs. Virtual agents in VRR use controllable motion models. Think digital puppetry for facial expressions, gestures, that's key for social cues. Wearable agents mostly advise us. They show things visually, tell us things verbally, or maybe trigger actions on our phone or smart devices. And there's a trend towards mixed initiative interaction, where the agent tries to predict when we need help, not just wait to be asked.
Proactive help again.
Right. And robotic agents, they directly control hardware, motors, joints, either at a very low level, like specific joint angles, or more abstractly, like move hand to this point.
Mm-hmm.
And there are underlying safety controllers making sure movements are smooth and safe.
And tying all this together, perception, modeling, action, is memory, right? They have to remember things to build that persistent understanding.
Absolutely essential. Memory captures the history of interactions, helps consolidate that internal world model. There's often talk of working memory fast, short term, maybe like a transformer's attention cache. And external memory slower, larger storage, maybe using techniques like RAG, retrieval augmented generation, to pull in vast amounts of information when needed.
And why is memory so critical?
Two big reasons are personalization, the agent learning about you over time, and lifelong training. That's the dream of agents continuously learning from experience without catastrophic forgetting and doing it efficiently so memory doesn't just balloon infinitely. How to store and update world models efficiently is a massive design choice.
Okay, this is incredibly complex stuff. How on earth do researchers measure if any of this is actually working? How do you benchmark an AI's understanding of the world?
Yeah, evaluation is really, really hard. There isn't one single test. Researchers use various benchmarks, each targeting specific aspects. For example, there's the Minimal Video Pairs benchmark, MVP. It tests physical and spatiotemporal reasoning using videos. The trick is, it uses pairs of videos that are almost identical but require different answers. This stops models from just latching onto superficial cues.
Clever. How are models doing?
Not great, honestly. Current models score around 40% accuracy. Humans get over 90%. So a huge gap in basic physical reasoning from video.
Wow. What about more fundamental physics, like do objects continue to exist when hidden? That kind of thing.
That's what InFIS2 looks at: intuitive physics, permanence, solidity, continuity. It shows plausible versus implausible scenarios, like an object vanishing or passing through another. And again, models really struggle, often performing near chance level. Humans find it obvious. It shows AI lacks core common sense about how objects behave.
They're resisting the basics. Okay, what about cause and effect?
That's tested by causal VQA. It asks causal questions about videos, counterfactuals, what-ifs, hypotheticals, predicting what happens next, planning. And again, state-of-the-art models are way behind humans, especially on predicting outcomes or reasoning about hypothetical situations. They're not yet connecting cause and effect robustly.
And for those wearable agents, the coaching and tutoring aspect, how do you measure if they're good at guiding us?
Right, that needs different tests. The World Prediction Benchmark is relevant here. It focuses on high-level action planning and long-term procedural understanding. Tasks involve identifying the correct next step in a sequence or choosing the right overall plan. It uses action equivalents, different ways to achieve the same goal, to force deeper reasoning.
And the results?
Humans are near perfect, the best models. Around 57% accuracy on one part, World Prediction WM, and only 38% on another harder part, World Prediction PP. So yeah, guiding complex human actions reliably, still a long way off.
Okay, so the benchmarks show clear challenges, lots of room for improvement. This isn't just about scaling up current models, is it? It sounds like we need new ways for AI to learn. What are the big future directions here?
Definitely not just about scale. The ultimate aim is autonomous learning. AI systems that learn continuously from their experience, adapting like animals do, not just in distinct training phases. The paper sort of groups current learning approaches into two main systems, System A and System B.
Oh.
System A is learning from observation. Think self-supervised learning on huge video data sets, just watching and finding patterns. Its strength is scalability, discovering abstract concepts from data. But it needs massive amounts of curated data. It doesn't know what data is important to learn from, and it struggles to tell correlation from actual causation.
Right. Just because two things happen together doesn't mean one caused the other.
Exactly. Then there's System B, which is learning through action. Reinforcement learning is a prime example. Learning by trial and error in the environment. Strengths. It's grounded in control, good for real-time behavior, can find novel solutions. But it can be very slow to learn, sample inefficient, struggles with complex environments, and really depends on getting the reward signal right.
So one watches, one does. The future must be combining them.
That's the vision, yeah. An integrated system. System A observation could provide structure, useful representations, making System B's job action easier. And System B, by acting in the world, could gather better, more relevant data for System A to learn from, grounding those abstract representations. It's this bidirectional pathway perception informing action and action guiding perception that researchers hope will lead to truly autonomous adaptive learning.
A learning loop, basically. That sounds powerful. What about multiple agents, AI teams?
Yes, multi-agent interaction is another huge area. The potential for collaboration is immense. Imagine teams of robots coordinating for disaster relief or fleets of autonomous cars negotiating traffic.
Or even on a personal level.
Sure. Maybe your smart glasses, smartwatch, and, I don't know, haptic feedback vests all working together seamlessly. Or in VR, having multiple virtual agents, assistants, NPCs collaborating in complex ways to make the environment feel incredibly real and dynamic.
But making them work together effectively must be hard. What are the main hurdles?
Key challenges are communication, coordination, and conflict resolution. Communication. How do agents share info effectively, especially when things are uncertain? How do they convey intentions, maybe even develop their own signals? Coordination. Syncing up actions, avoiding stepping on each other's toes, sometimes literally,
Yeah.
making decisions together, maybe with limited information, and conflict resolution. What happens when goals clash or they physically interfere? They need ways to negotiate and compromise without a human stepping in constantly.
It sounds like they need social skills, almost.
In a way, yes. And that brings us to human-agent interaction, too. It's not just about agents talking to each other, but to us. That requires social intelligence, reading human emotions, intentions, responding appropriately using verbal and nonverbal cues effectively, building trust, basically.
Okay, this is all incredibly powerful stuff, which inevitably brings us to the ethical side. As these agents get woven into our lives, what are the big red flags we need to watch out for?
Absolutely crucial conversation. The paper flags two major areas of concern right now: privacy and security, and the risks of anthropomorphism.
Let's take privacy first. Smart glasses seeing everything, home robots hearing everything. That sounds like a privacy nightmare waiting to happen.
It's a huge concern. These agents, by their nature, have access to incredibly sensitive personal data. Conversations, habits, private moments. Protecting that data is paramount. How is it stored? Is it encrypted on the device? What happens when models are updated centrally? Techniques like federated learning help keep data local, but even that might need extra layers like differential privacy, which can sometimes hurt accuracy. It's a trade-off. A key challenge is ensuring agents only collect and use data that's strictly necessary data minimization and preventing leaks. This is a very active research area for responsible AI development.
Right. Keep the data locked down and only use what you absolutely need. Okay, what about the second point, anthropomorphism? Giving AI human-like qualities. Why is that risky if it makes them easier to interact with?
It's a double-edged sword. Making AI relatable can be good, but it brings risks. First, users might overestimate what the AI can actually do. This illusory agency can lead to disappointment or even unsafe situations if you rely on it for something it can't handle.
Expecting too much.
Exactly. Second, a very human-like design can hide the fact that it is a machine. It obscures limitations, makes its decision-making process unclear, and that can erode trust in the long run. We need transparency.
So we might forget it's a tool and treat it like a person, leading to problems.
Precisely. Third, an AI using emotional language or nudging you towards certain actions could subtly manipulate your behavior, maybe in ways you wouldn't choose yourself. And fourth, if you get used to a very human-like interaction, you might get frustrated when the AI inevitably fails to respond like a real person would in some situations.
So how do we mitigate that?
It's about responsible design, being clear about what the agent can and can't do, using design patterns that are helpful but don't intentionally deceive users about the AI's nature, and, importantly, educating people on how to interact with these systems realistically. And of course, beyond these two, all the other foundational AI ethics issues still apply. Aligning AI with human values, tackling bias and discrimination in models, dealing with hallucinations. It's a broad and ongoing effort.
What an incredibly thorough deep dive. We've really covered the landscape of embodied AI agents, from what they are, virtual, wearable, robotic to their brains with complex world models, how we measure their progress, where the research is heading with learning and collaboration, and finishing with those really critical ethical considerations. It's undeniable that these agents could fundamentally change how we interact with technology, making it feel much more intuitive, more responsive, more present. So maybe the final thought to leave everyone with is this. As these intelligent agents keep blurring the lines between machine and, well, us, what new kinds of companionship, productivity, even learning might we unlock? And perhaps more importantly, how do we make absolutely sure they end up serving our genuine human needs and well-being?